When we usually think about advanced artificial intelligence, there's this very specific, almost industrial image that comes to mind.
Oh, totally. Like a massive warehouse.
Right, exactly. A warehouse-sized data center.
Yeah.
Rows and rows of server racks, blinding LED lights, the deafening roar of those massive industrial cooling fans. We've kind of been conditioned to believe that true intelligence requires that kind of massive, centralized real estate.
Yeah, it really has felt like the mainframe era all over again. We've just sort of accepted this premise that the quote-unquote brain of the operation has to live somewhere in a cold room in the desert.
Yeah.
And our personal devices, like the laptops and phones we use every single day, they're essentially just dumb terminals. Like, we send a question out into the void, and then we just wait for the supercomputer to send an answer back.
But today, we are going to completely dismantle that image. So, welcome to this deep dive. Today, we're exploring this massive stack of technical reports, benchmark data, and clinical case studies, all centered around what looks like a structural inflection point in open-source AI.
A huge one.
Yeah. We're looking really closely at Google DeepMind's Gemma 4 family, which just dropped in April 2026. And our mission for you today is to understand how this tech is physically moving out of those giant cloud data centers and, well, directly into the devices in your pocket.
Right onto the edge.
Exactly. Because it is completely rewriting the rules of privacy, of hardware constraints, and just generally how we solve complex problems.
Yeah, and if you look at the visual backdrop of our discussion today, the sort of hybrid of towering server racks blending seamlessly into edge devices like smartphones and medical sensors, it perfectly captures the physical transition we are analyzing here.
It really does.
But to actually understand why Gemma 4 matters right now, we have to start with a shift that, honestly, it sounds a bit mundane on the surface.
Right, the legal stuff.
Yeah, but it's actually a tectonic shift for the entire industry. I'm talking about the licensing.
Because previously, open source models came with like a lot of strings attached, right?
Yeah.
You couldn't just take them and do whatever you wanted.
Oh, far from it. Previous generations used these highly scrutinized so-called acceptable use licenses. And if you think about this from a business perspective, it's a nightmare.
How so?
Well, say you are a Fortune 500 company or even just a smaller enterprise. Building your mission-critical infrastructure on a model where the creator could just, unilaterally revoke your access if their corporate policy is shifted down the road.
Oh, yeah, that's an uninsurable risk.
Exactly. It was a massive compliance bottleneck. And that kept the really big players tied to the cloud. But with Gemma 4, Google executed this really aggressive shift to a universally permissive Apache 2.0 license across the board.
So no more strings?
None.
Meaning literally anyone, from a solo software developer in their garage to an entire sovereign nation, they can build secure, completely off-the-grid infrastructure without constantly looking over their shoulder to see if they're, breaking terms of service.
Right. It fundamentally allows enterprises to establish true digital sovereignty. They can build their core intellectual property securely, knowing the ground won't just suddenly shift beneath them. It completely commoditizes the foundation.
Okay, so the legal barriers are gone. That makes sense. Let's lift the hood here and look at the physical barriers, because to understand how we are running these incredibly capable models on a standard laptop or a phone, without melting the hardware.
Right, without starting a fire.
Yeah, exactly. We need to dive into the foundational architecture.
Yep.
And I actually want to start with the 26 billion parameter model, the 26B-A4B.
Okay, yeah. Good place to start.
So the documentation says this uses a mixture of experts, or MOE configuration. For anyone listening who isn't a machine learning engineer, how does this actually rewrite the rules of efficiency?
So to appreciate the mixture of experts architecture, we kind of have to understand the traditional alternative, right? Which is a dense model.
Okay.
In a dense model, every single artificial neuron or parameter fires every single time you ask it a question.
That sounds exhausting.
It is. It's incredibly computationally expensive. But what MOE does is decouple the model's total knowledge from its active computational costs.
Okay, wait, explain that.
Sure. So the 26B-A4B model has 25.2 billion total parameters. Think of those like synapses in a brain, right?
Got it.
But during any given execution, what we call a single forward pass, or basically one cycle of calculating an answer, It only activates 3.8 billion of them.
Wow, that is a massive reduction. So it holds this vast amount of knowledge, but it only uses a tiny fraction of it in the moment.
Exactly.
But how does it know which parts to turn on? Like, how does it pick?
Well, it uses this highly optimized routing mechanism. Deep inside the model, there are 128 distinct expert neural networks.
Okay.
And when you give it a prompt, the router looks at the data and sends it through just 8 active experts per token, plus 1 shared expert.
Oh, a shared expert. What does that do?
That shared expert is crucial. It acts as an anchor. It holds universal contextual data so the specialized experts don't, lose the plot entirely.
Oh, I see.
And the architectural benefit of doing this is staggering. It captures about 97% of the cognitive performance of the massive flagship 31 billion parameter dense model.
But it uses way less power.
8 times less compute power, yeah.
Which means it's hitting the absolute sweet spot for local enterprise deployment on a single GPU. Like, you don't need to rent $1 million server rack anymore.
Nope, you just need a solid, high-end workstation sitting in your office. You're bringing server-grade reasoning directly to the local network.
Okay, I follow that for the larger models, but I want to look at the really tiny ones for a second.
The edge models.
Yeah, the sources detail the E2B and E4B edge models. And I noticed the E stands for effective parameters. And they point to this new mechanism called per-layer embeddings, or PLE.
Oh, PLE is fascinating.
Well, I have to admit, reading the math on this made my eyes cross for a second. So let's ground this. Why is standard embedding a problem for these small models in the first place?
Okay, we can break it down by looking at how an AI actually reads. Because when you type a prompt, the AI doesn't see English words, right?
Right, it sees numbers.
Exactly. It uses an embedding layer to translate those words into a massive grid of numbers. It's a mathematical representation of the meaning and position of your text.
Okay.
Now, in traditional models, all that semantic data is packed into one massive upfront embedding sequence. But as that data moves deeper and deeper through the model's decoder layers,
The logic steps.
right, the sequential steps of logic the AI takes to formulate an answer, well, that initial embedding has to retain everything all the way through.
Oh, I see. So it creates an informational bottleneck.
Yes, exactly. The deeper the logic goes, the harder it is for a small model to hold onto the specific, highly detailed nuances from the very beginning of your prompt. It just starts to get fuzzy.
Okay, wait, let me see if I have this right. Is traditional embedding essentially like trying to memorize an entire dense textbook right before you walk into a final exam?
Oh, that's a good way to look at it.
Right, like you're just hoping you remember the obscure details by the time you reach the last page of the test. Whereas this new PLE system, per layer embeddings, is more like having someone slip you a highly specific cheat sheet exactly when you reach each specific question.
That is a phenomenal analogy. Yes, that captures the mechanism perfectly.
Okay, cool.
Yeah, PLE creates a secondary, entirely distinct embedding table. So instead of forcing the model to remember the whole textbook up front, it feeds a specialized, incredibly small residual signal directly into every individual decoder layer along the way.
So it's giving the AI little reminders.
Reminders that are mathematically tailored to that exact stage of computation, yeah. Each network layer gets an independent channel to process token-specific information exactly when it becomes relevant to the inference chain.
Oh, wow.
And because the digital footprint of this PLE signal is tiny, you get specialized, high-resolution intelligence at every single layer without bloating the overall size of the model.
That makes so much sense. It's basically just-in-time information delivery.
That's nice.
But having that deep understanding at every layer creates a new physical problem, doesn't it?
What do you mean?
Well, if the AI is suddenly retaining all this specific information beautifully, what happens when we feed it an absolute mountain of text? Because the sources say these models can hold 256,000 tokens in their working memory.
Yeah, the context window is huge.
And for you listening, that's like feeding the AI an entire 800-page book at once.
Okay.
Keeping that much data active usually crushes a computer's RAM.
Yeah.
How are they solving that memory bottleneck?
Right, so they tackle it with 2 primary mechanisms, the shared KV cache and PRO E.
Let's do the cache first.
Okay, so the key value, or KV cache, is essentially the AI's short-term memory. It holds the context of everything it has processed so far.
Right.
But as the context gets longer, like reading that 800-page book, that cache scales exponentially, becomes a massive memory hog.
Right.
So Gemma 4 implements a shared KV cache optimization. Basically, the final layers of the model stop computing independent key and value projections. Instead, they dynamically reuse the tensors, which are just the multi-dimensional grids of numbers holding the context. They reuse them from the last non-shared layer.
Wait, hold on. I have to jump in here and challenge this.
Go for it.
If we're just reusing old data tensors at the very end of the process simply to save memory space, aren't we basically giving the AI amnesia for the middle of the book?
Ah, I see what you're getting at.
Right. Like, it sounds like we are forcing it to just skim the end of the document, which means it would lose crucial fine-grained details in a 256,000-word file.
It's a very valid concern, and actually that's exactly what happens in poorly optimized models. But it's where the Gemma 4 architecture really shines.
Okay, why?
Because they don't just reuse data blindly, they use a highly complex hybrid attention mechanism. What it does is interleave local sliding windows with full global attention.
Okay, what does a sliding window look like in practice?
Imagine the AI has a magnifying glass, right?
Sure.
The sliding window only looks at a small chunk of text at a time, say the previous 224 tokens. It moves that magnifying glass along as it reads, which saves massive amounts of memory because it isn't trying to hold the whole book in hyperfocus at every single second.
But then how does it remember the overarching plot?
Right. So to prevent the amnesia you mentioned, it weaves in global attention layers periodically. Those look at the entire document to maintain the plot. And the crucial design choice here is that they guarantee the absolute final layer is always global.
Oh.
Yeah, so the very last step of logic always captures the ultimate contextual relevance.
That is incredibly elegant. Wow. And what about the second mechanism, the P-rho-PE?
Yeah, P-rho-PE. That stands for proportional rotary position embedding.
Okay, that's a mouthful.
It is, but think of it as the map coordinate system for that massive 800-page book. It elegantly scales the positional data so the model knows exactly where every single word is located in that 256K context.
So it doesn't get lost.
Exactly, and it does it without requiring the hardware to hold an infinitely expanding map in its active RAM. The ultimate performance impact of combining these two things is that you can process massive, highly detailed documents locally without the model hallucinating, losing the plot, or, crashing your computer.
Okay, so we have these massive architectural efficiencies in memory and processing. And as I'm reading through these benchmarks, it becomes very clear that all of this efficiency wasn't just engineered to make the model run faster.
No, not at all.
It was designed to give the model the cognitive headroom to do something fundamentally different, to pause and actually think.
Yes. This is the true paradigm shift of the Gemma 4 family. We are talking about the native integration of a configurable reasoning mode.
It's activated by a specific command, literally called the think token, right? It looks like an HTML tag almost.
Yep, the think token.
And when you engage this, the model fundamentally alters how it answers you. Like, it stops being a snappy chatbot that just guesses the next word instantly. Instead, it enters a prolonged chain of thought phase.
It generates a silent internal monologue.
Exactly. It explores math algorithms, it tests logic, and verifies its own work inside a hidden thought block before it ever shows you a single output word.
And what's fascinating here is how this shifts the fundamental economics of AI computation.
What do you mean by economics?
Well, historically, AI models relied almost entirely on training time memorization. Companies spent hundreds of millions of dollars up front in massive data centers to train the model to recognize patterns so it could answer instantly.
Right. All the heavy lifting was done beforehand.
Exactly. But this reasoning mode shifts the computational burden to inference time reasoning. Inference being the moment you actually ask it a question.
Oh, meaning it spends compute power proportionally to how hard this specific question actually is.
Yes.
So if I ask it the capital of France, it answers instantly. If I ask it to solve a calculus problem, it sits back and works it out.
It scales its cognitive effort based on the difficulty of your prompt.
But, I mean, there is a massive real-world trade-off here, the latency.
Oh, absolutely.
Because a model might sit there and generate 4,000 internal tokens of thought before outputting its final answer to you. We're talking about a time to first answer latency that can stretch into seconds.
Yeah.
10, 15 seconds of dead silence.
Which feels like an eternity in tech.
Right. That fundamentally shifts the user experience. You aren't texting a friend anymore. You are submitting a job to a high-latency, asynchronous computational engine.
It is a deliberate sacrifice of speed for accuracy. But if you look at the benchmarks, they prove unequivocally why that trade-off is worth it.
Like the AIM math benchmark.
Exactly. The AIM 2026 math benchmark is notoriously difficult. The previous generation, Gemma 3, scored 20.8%.
Ooh.
Yeah. But the Gemma 431B model, utilizing this deep thinking mode, hit 89.2%.
89.2%. I mean, that's not an incremental update. That is an absolute obliteration of the previous standard. It completely obsoletes the older generation in high-end logical applications.
It really does. But, if we step back for a second, this creates a massive physical contradiction.
How so?
Well, we are talking about an AI doing intense multi-step logical reasoning, right?
Yeah.
If my smartphone tries to churn through 4,000 internal thoughts before answering a text, it's going to literally melt the battery and grind the processor to a halt. So how did Google actually fit this into an edge device's silicon?
That brings us to the fascinating world of hardware co-design. Because, yeah, a brilliant software model is essentially useless if your physical device can't actually run it.
Exactly.
And the sources detail how Google achieved day zero hardware optimization. They didn't just build the model and hope hardware caught up. They designed it hand in hand with the chip makers.
Right, like the mobile stuff.
Yeah, for mobile devices, they utilize something called ARMv9 SME2 instructions.
So to understand SME2, imagine a highway. Traditional math processing on a phone is like a single-lane road. It gets congested quickly.
Sure.
SME2 basically acts like a 16-lane superhighway, specifically for matrix math. It allows the phone's processor to compute massive chunks of the model's neural network in parallel simultaneously instead of one by one.
And the results are just incredible. It gives the tiny E2B Edge model a 5.5x speedup in the prefill stage natively on Android smartphones.
Wow.
Meaning it can ingest an 800-word block of text in under a second directly on your phone's standard processor.
And it's not just phones either. Apple Silicon users got native MLX framework integration with a feature called TurboQuant.
Okay, what is TurboQuant?
So TurboQuant uses sub-byte quantization, which is really just a highly technical way of saying it shrinks the physical space a number takes up in the computer's memory, like shrinking it from a sprawling house down to a tiny apartment.
But without losing the math precision.
Right, without losing the precision.
Yeah.
This reduces memory consumption by a factor of 4x for Mac M3 Ultra desktops.
The major takeaway for you listening to this is the freedom it provides. You can process highly complex, reasoning-heavy tasks entirely locally, no cloud offloading, zero network latency, and total airtight privacy because your data literally never leaves the physical metal of your device.
And having that level of local power is what makes the next major piece of this release so impactful. The Agent Development Kit, or ADK version 1.0 Levo.
Yes,
Yeah.
because it's one thing to have an AI that can think quietly to itself, right?
Yeah.
But developers need tools to turn this thinker into a doer. They need it to actually take actions.
Right. And the ADK transforms Gemma 4 into the cognitive engine for autonomous multi-step software agents. But to make it efficient, it establishes a strict hierarchy to prevent what they call token waste.
Token waste.
Yeah, which is essentially just burning expensive computational power on really simple tasks.
Okay, let me see if I have the analogy right for this hierarchy, because it totally fascinated me.
Let's hear it.
The ADK separates things into two main categories: workflow agents and LLM agents.
Right.
This is basically like running a corporate office. Like the workflow agents are the strict, slightly rigid middle managers. They handle the deterministic routine schedules, the basic yes or no routing, and they are incredibly cheap to employ. And the LLM agents are the highly paid, expensive creative consultants who only get called into the boardroom for the non-deterministic, complex problem solving.
You hit the nail on the head. That's exactly it. You don't use your expensive, computationally heavy LLM to decide if an email should go to the sales folder or the support folder, right?
You'd be wasting resources.
Exactly. You let the deterministic workflow agent handle that simple routing. But when the system encounters a novel problem, say an angry customer email that requires a nuanced, empathetic response and a customized discount code.
Then you call in the big guns.
Right. The middle manager escalates it to the LLM agent to think through the solution.
And the ADK gives these agents real power. They can navigate REST APIs, modify files, send emails, which, if we are being honest, sounds slightly terrifying if an autonomous agent goes rogue or just misunderstands a prompt.
Oh, it's a profound security risk, which is why the ADK natively includes human-in-the-loop workflow.
Okay, good.
If we go back to your corporate office analogy, the human-in-the-loop is the CEO. If the agent is about to execute a high-stakes action, like initiating a financial transaction, deleting a database, or making some destructive API call it pauses, it physically cannot proceed until it solicits and receives explicit human confirmation.
It's a mandatory safety net.
Exactly.
And beyond safety, they also solve the continuity issue.
Yeah.
The ADK uses state and session management tied into Google Cloud's Firestore.
Right.
So these agents actually have persistent long-term memory across disconnected sessions. You can collaborate with your local AI today, close your laptop, fly across the country, open it up next week, and it remembers exactly what you were working on and the context of all your previous decisions.
Which is huge. And this functional autonomy raises a really important point about where this technology is actually going to be deployed.
Yeah.
Because we've established the theoretical power of local reasoning AI. But the most profound applications of this tech aren't happening in a Silicon Valley server room or even in a traditional corporate office.
No.
They are happening in the real world, particularly in off-grid healthcare environments.
This was easily the most incredible part of the research stack for me, because we are talking about literal life or death scenarios where a reliable internet connection might not even exist. The Epicast deployment in West Africa is the perfect example of this.
Oh, Epicast is phenomenal. It's a real-world application of the E2B Edge model we discussed earlier.
Yeah.
Healthcare organizations deployed it specifically to bridge critical infrastructure gaps where cloud connectivity is simply non-existent.
Wow.
They took this tiny local model and fine-tuned it to work directly alongside hardware sensors, specifically visual arrays like Medsaclip and acoustic sensors like HERE.
Wait, so the AI can physically see and hear the patient?
It can. It empowers local community health workers to capture completely unstructured clinical observations. So a worker can record a patient's visual symptoms, like a rash, or capture the specific sound of a patient's cough.
That's amazing.
And the AI processes all of this while the patient speaks in local dialects.
And here's where it gets absolutely incredible. It processes all of that completely offline, right there on the device. It translates those messy real-world symptoms into standardized World Health Organization disease surveillance signals. It detects localized disease outbreaks like respiratory infections, ultra-early, entirely off the grid. He doesn't need to ping a server in California to figure out what's happening in a remote village.
It's taking frontier-level intelligence and pushing it to the absolute edge of human need. And, we see similar transformative approaches in advanced clinical patient care tasks as well, just in different contexts.
Right, like the sources detail personal health agents or
Sure.
PHAs.
Yeah.
By securely ingesting wearable biometric data from devices like Fitbits, the local AI acts simultaneously as a specialized domain expert, a data scientist analyzing your sleep and heart rate trends, and basically a holistic health coach.
All locally.
Exactly. It tracks your preventative care over months and years without ever needing to send your intimate heartbeat data to a tech company's centralized server.
And then, in high-end, heavily regulated hospital environments, they are deploying it for clinical workflow automation. Gemma 4 models are placed locally on machines locked securely behind the hospital's strict firewall.
Because of privacy rules.
Right. And these local models are powerful enough to parse highly dimensional imaging, like massive 3D CT scans and MRIs. They perform complex anatomical localization and streamline clinical documentation.
Because again, thanks to that universally permissive Apache 2.0 license and the intense hardware co-design we talked about, the hospital doesn't need to risk sending highly sensitive patient MRIs out to a third-party cloud. The analysis happens right there in the building instantly.
Exactly. And, if we synthesize everything we've unpacked today, it becomes really clear that Gemma 4 is not just an incremental software update.
No, it's a structural pivot for the entire ecosystem.
Yeah.
I mean, by blending per-layer embeddings, the incredible efficiency of the mixture of experts architecture, those native thinking paradigms we talked about, and aggressive hardware co-design, we now have high-fidelity, autonomous intelligence living directly on our personal devices.
And that leaves us with a critical, almost uncomfortable question for you to ponder.
Let's hear it.
The Apache 2.0 license has effectively commoditized the edge. If every smartphone, every laptop, and every local workstation can now reason, code, and diagnose diseases at a frontier level entirely off the grid, well, what happens to the multi-billion-dollar business model of the centralized cloud?
Wow.
Will the future of the internet be less about paying a subscription to connect to a supercomputer and more about carrying one in your pocket?
We started this deep dive talking about that massive humming data center, the size of a football field. It turns out the future of AI isn't about building bigger rooms. It's about realizing the room has already been folded up, handed to you, and slipped right into your pocket. Keep questioning, keep learning, and we'll catch you on the next deep dive.